you are able to observe. So let me see where I put this down so that you can collect it. So it depends on the form we are able to um, I mean the form of the equation. So let's look at different situations now. Then we'll see some examples on that where still from this number 8 we see some of them that are not exact. Don't forget that we examined Roman figure 1 earlier. In Roman figure 1 we saw that this was not exact because the derivative of this with respect to y was 1, derivative of this with respect to x was -1, so they were not equal, so which meant that this equation was not an exact equation. Of course, it's still not an exact equation. So when we have some situations like this, we may be able to multiply the expression through, we may be able to multiply the equation through with some function. Then when we multiply it through with that function, the equation will now become an exact differential equation. So there are cases like that. So that function that we will use to multiply this equation, so that this equation that is not exact before will then become exact, is usually called an integrating factor. So we will look at it now. An integrating factor denoted as I of x comma y. So we may be able to get, I'm emphasizing may because it may not be possible in some situations, but usually you'll be given a problem where it is possible for you to do it like that. So we may be able to get an integrating factor for that differential equation that is not exact, such that we will now multiply it through by that integrating factor, and then it will become exact. Then we will solve it as an exact differential equation. It becomes very, very easy to solve that way. So let's see, how do we get this integrating factor? That's the question now. So we now say that we have three conditions here, and the first one is that if, so I'm reading this, I'm taking this from your lecture notes you have been given, the materials you have been given. So this, if 1 over n, of course our n, as usual, of course you will have the differential equation to be in this form: m of x comma y dx plus n of x comma y, okay, plus n of x comma y plus n of x comma y dy to be equal to 0. That's the general form of the differential equation. Now we are now saying that, of course, this is our n, this is our n, this is our m. Okay, so we're now saying, now we know that firstly we are checking del m of x comma y del y to see if it is equal to del n of x comma y del x. Normally if it is exact, these two will be equal, but of course it is not exact, so they are not going to be equal. That means it is not exact. Okay, not exact or inexact differential equation. So this is applicable to, what we want to do now is applicable to inexact differential equations. So you have them in this form, but you check this condition and it doesn't hold, then we may be able to get an integrating factor. So how do we go about getting that integrating factor? We now check this condition. We now say, okay, the first one to check is if 1 over n into del m del y minus del n del x, still the same thing here that we have, if we bring them together and multiply them by 1 over n, if it is going to give us, but as if it's equivalent to some function that depends only on x. Now we know that these two depend on x and y. These two depend, each of them depends on x and y. So, but if we bring them together, then do a subtraction, then multiply it by 1 over n, and then at the end of the day we get a function that depends only on x. Then we can get an integrating factor, I of x comma y, which is given by exponential or e raised to power integral of g of x dx. Don't worry, we're going to solve some problems. You see how this works. Okay, so that's case one. Another case is this. If we check this second condition, that is if 1 over m into del m del y minus del n del x, okay, if it is equivalent to some function that depends only on y, h of y. That means at the end of the day, by the time you do this, now you are multiplying it by 1 over m, and then you get a result that depends only on y. Then you can get an integrating factor I of x comma y, which is given by e raised to power minus integral of sorry, in this case h of y dy. Okay, then finally we have another condition that you need to check to see if it can be made an exact differential equation. We say that if m is equal to, again I said this is from your lecture material directly, if m is equal to y of f of xy. So f of xy is not the same as f of x comma y. F of xy means that the terms are xy only. That means you have the product terms xy only. Okay, if m is, or can be written as y multiplying some function that depends only on xy, then and n can also be written as x multiplied by some function that only depends on xy, that is, has only xy as its variable. Then we can get our integrating factor I of x comma y, which is given by 1 over xm minus yn. All right, so those are the three situations we check. So if it happens that we go with this first, if it happens that we're able to get something like this that depends only on x, so don't forget that a constant can also be said to depend only on x. You can have this to be a constant at the end of the day. Maybe you get this and all of this, you do everything here and then you get 1. It is still correct. It's also correct for this, but then we usually go with this first. So we check this first. If it's a function that depends only on x, or is some constant, then we are good to go. We will get our integrating factor this way. If it's a function that depends only on y, then we'll get our integrating factor this way. If it doesn't satisfy any of these conditions, then we check if it satisfies this, then we use this as our integrating factor. If it doesn't satisfy all of this, that means we cannot get an integrating factor for that inexact differential equation. Of course, you will not come across that in this course, but that is that as far as the scope of this course is concerned. So now we're good to go. So let us check for this first equation that we had, that we established was not an exact equation. So let's do that on the next sheet. So that equation, that's number one problem here, was y dx plus x dy equals, sorry, it wasn't plus, y dx minus x dy equal to 0. So we have established that, of course, in this case, our m of x comma y is equal to y, and our n of x comma y is equal to minus x. So we've established before that this is del m of x comma y is equal to 1, of course, partially with respect to y, and then del n of x comma y with respect to x is equal to minus 1. Of course, they are not the same, so that means that it is not exact. Then we will now consider if we can get an integrating factor, so that we multiply it through with that integrating factor, and then it becomes an exact differential equation. Then we can solve it using our usual method for exact differential equations. So the first thing we check, as I've just said now, as we wrote here earlier, is we're going to check this, if this is going to hold, if this is going to be some function that depends only on x. So let's do that now. We already got our del m of x comma y del y and our del n of x comma y del x. So we bring them together. So we now say that, okay, of course these two are not equal, but we now check for del m of x comma y del y minus del n of x comma y del x. So don't get it twisted. This is still, y is not in, just to make it compact, that's why that's why bracket of x comma y is not included in all of this. But of course, it doesn't make any difference now. So when you subtract these two, you're going to have this to be, okay, so let's just divide it directly. What we want to get is 1 over n multiplying this. So let's do that. So this is going to give us 1 over n of x comma y. So that's what we want to do. Then multiplying this. So that is going to be, so what's our n of x comma y now? Minus x. So that is going to be 1 over minus x, okay, into brackets this. So 1 over minus x, and then the lem of x comma y, del y, that is 1. So that's going to be 1. Then minus the ln of x comma y, then the y, that's the x, that is minus 1. So that's what we have from that. And then this is going to give us minus 1 over x, then into, this is going to be 1 plus 1, which is 2. So basically what we have here is minus 2 over x. So obviously this is a function that depends only on x. So that means our first condition here is satisfied by this function. That means that indeed we can get an integrating factor, okay, with which we will multiply the given equation, so that the given equation will become an exact differential equation. So let us do that now. So they said that the integrating factor, we said, will be given by e raised to the power of integral of g of x dx. Don't forget what g of x is. That expression we just found now by doing this arithmetic. So that's what we just obtained here. This is the expression for our g of x. So now we are suggesting that the integrating factor, which is going to be, or could possibly be, some function depending on both x and y, is going to be equal to exponential, or into e raised to the power integral of g of x, okay, dx. So that is going to be e raised to the power integral of g of x is minus 2 over x, then dx. So we're doing the integration here. So this is going to be equal to e raised to power. So what's the integral of this? Of course, minus 2 is a constant. You can move it out just to simplify this a bit. Integral of 1 over x dx. So we all know that integral of 1 over x is ln x. So this is e raised to power minus 2 ln x. Hope you got that. So, but here we usually let go of the constant sign, I mean the constant of integration. So forget about the constant of integration here. So that's just going to complicate the issue. So we just forgo it. So that is how to solve this kind of problem. Let's go of that constant of integration, and then we can say that this is e raised to power ln, from our rules of logarithms, ln is log to base e. So from our rules of logarithm, when you have this as your coefficients, it can become a power to this. So this is going to be x raised to power minus 2, and of course this is going to be e, or this is just e raised to power log x to power minus 2 to base e. So this e raised to power, we cancel the log here. So this is just going to be x raised to power minus 2, or if you like 1 over x squared. All right, so that is our integrating factor. So what is the use of integrating factor again? I said that this means that we can multiply the original equation by this. We'll multiply the original equation by this here, and the original equation will now become exact. So let's see. Is that true? So let's multiply this equation all through by 1 over x squared. Oh, sorry. My papers are falling. Let me just spark that off. Right. So when I multiply this all through by 1 over x squared, what is it going to give me? So let's see. This is y dx minus x dy. I hope you can see that on the screen, and let me just write it out first. So it's equal to 0. So when I multiply it through by my integrating factor now, I'm going to have this to be 1 over x squared multiplied by y, 1 over x squared multiplied by y dx minus, that will be still 1 over x squared multiplied by x dy is equal to 0 multiplied by that, that's still 0. So this is going to give me y over x squared dx minus 1 over x. That's going to give me x, we cancel this 1 over x dy is equal to 0. So let's check, is this now an exact differential? So of course, as before, we will check when you, so that means our new m of x comma y is now this, our new n of x over y is now this. When I differentiate this partially with respect to y, what am I going to get? I'm going to get 1 over x squared when I differentiate partially with respect to y. And then when I do that for this partially with respect to x, you know, derivative of minus 1 over x, okay, the x of this, if I want to differentiate this, I'll say del y del x of this. Okay, what is it going to give us? We're going to use our quotient rule. Bottom the top, okay, that's going to give us 0, minus top the bottom, that's minus of minus 1. The derivative of the bottom is 1 all over the bottom squared. So this is going to give us minus of minus 1, 0 minus of minus 1, that is going to be 1 all over x squared, which is the same as when you differentiate this partially with respect to y. So we can see that our equation, which was initially not exact, has now become an exact differential equation, and we have not broken any rule because we just multiplied an equation through by this expression, and so we are good to go. And so far, of course, in this case x is not 0, but just leave that out now. Okay, so we can now solve this differential equation as before. There's no need to go through that long process. We can now say that, okay, let's integrate this partially with respect to x. Okay, don't forget that what we have here is simply y x to the power minus 2. Okay, we want to integrate that partially with respect to x. So let's minus 2. So let me write it this way: the x, then minus 1 over x dy equal to 0. So integrating this partially with respect to x, it will give me y x raised to power minus 2 plus 1 all over minus 2 plus 1. I hope you got that. So, and then for this, integrating this partially with respect to y, that's just going to give me minus 1 over x, then multiply by y. You know, this is a constant. All right, so when I deal with this, this is just going to give me y x raised to power minus 1, then divided by minus 1. Of course, this is just going to be minus y x raised to power minus 1, which is the same thing as having minus y over x. So you can see the integral of this with respect to x gave me minus 1 over x. The integral of this also with respect to y gave me minus 1 over x. So in this case, they don't have any other term. This one does not have any other thing. This also does not have any other thing. So this is what is common to both of them. I'm going to write that out only once. That's going to be minus y over x. Then they don't have any other thing. So that's all I have here. Then plus constant of integration is equal to 0. So that will be our solution to the given differential equation. So life can be as easy as that. As easy as that. So, and if you like, you can make y the subject here. For instance, if you make y the subject, we're going to have something like minus y over x is equal to minus c, or just c, or anyhow you want to put it. So that means y is equal to some cx, and then if you differentiate now, the y, the x is going to be equal to c, some constants, okay, which you don't know what it is. And then so that is that about that. Yeah, I want you to quickly see something here. Actually, that's the fact that I told you something before, that if you are given this equation and obj and then you don't even know how to get this, in this case, this is an implicit function. So that means that in this case, that means we have some function. Okay, you can see that on the screen. Sorry. That means in this case we have some function f of x comma y, such that this is equal to minus y over x plus c equal to 0. when you take its that's the function itself. Then when you take its differential, the f of x comma y, that's going to be, that's going to be del f del y, let's take x first, del f del x dx plus del f del y dy to be equal to 0. But then don't forget, we have solved the problem already, so I'm just playing around with this so that you know how to play around with options if you are unable to solve this kind of problem in the example and you're given an OBJ question to solve. So if we differentiate this partially with respect to x, we're going to have bottom the top, that's going to be this derivative of the top partially with respect to x, that will be 0, minus top the bottom, that's minus of minus y, that's what you have at the top here, minus top the bottom, derivative of the bottom is derivative of x with respect to x, that's 1, all over bottom square, that will be x squared, then you have it as dx. Then when you differentiate partially with respect to what's it now, y, this is going to give you minus 1 over x, then you're going to have the y to be equal to 0. Okay, so at the end of the day, you're going to have this to be y over x squared dx minus 1 over x dy to be equal to 0, which is what we had here before as the exact differential equation that we came about. And of course, this could have also given us the original equation here if we just multiplied all through by x squared. So by simply multiplying all this by multiplying this through by x squared, okay, this is the equation now, you can see it on the screen. By multiplying this through by x squared, we're going to have this to be y dx, then minus, when you multiply this by x squared, it becomes x squared over x, that is x dy, then this will be equal to 0, so which is the equation that we started with. So that's how you can verify that whatever you have in the option is correct. That means if you're unable to get this, or you are not sure of yourself, you can always do this, get the total differential, that is let f be equal to what you just got now, this, and then get the total differential. The f will be del f del x dx plus del f del y dy equated to 0. Then try to get that from here. So at the end of the day, it should give you back the original equation. It should give you this this one that we made to become exact by multiplying through by the integrating factor, which you can also get the original equation just by clearing off the integrating factor. In this case, our integrating factor was 1 over x squared. Okay, our integrating factor was 1 over x squared. So if you multiply through by x squared to clear off the integrating factor, it should give you back the original equation. Our original equation was y dx minus x dy equal to 0, which is what we started off with. So life can be as easy as that. So to round off this portion of differential equation, let us pick another one that we know is not exact and see how we can make it exact. We check if we can make it exact, and then we'll make it exact if it is possible, then solve it. So let me pick the where I wrote the conditions so that I can make reference to it here also. So we say that, now look at number 8 that we are solving. Look at number 8, Roman figure 5. Number 8, Roman figure 5. It says that y squared minus y dx plus x dy, okay, is equal to 0. So that's the equation. So in this case, quickly, m of x comma y is equal to y squared minus y, and n of x comma y is equal to x. That's the coefficient of this, coefficient of this. And then when you differentiate del m of x comma y, I'm going to ignore having to write del m, having to write this bracket x comma y so as to make our writing compact and fast. So let's do this. Now this is going to be del, so we're going to differentiate this with respect to y. That's going to give us 2y. Then differentiate this with respect to x. So that's going to give us del n del x is equal to 1. Obviously, the two of them are not the same. So let's check if we can make it, and if we can get an integrating factor that we can use. So because they are not the same, that means that this is not an exact differential equation. So let's check if we can get an integrating factor that will help us solve this problem. So as usual, we'll check this condition first. So let's check for 1 over n into del m del y minus del n del x. Please always take note of this. So m is that coefficient of x, okay, and n is that coefficient of m is that coefficient of the x and n is that coefficient of the y. So just follow the arrangement like that. So whatever, if you are picking coefficients of the x, you are differentiating partially with respect to the other one, y. That's if you want to check if it's exact. So that means that if this was, let's say, t and this one was x, you would do the same thing. You are taking, that means if you add something like dt here, you will be differentiating this coefficient partially with respect to the other one, which will be x. So that means that now let's check this, if this is going to give us some function of x, and then we will be able to get an integrating factor, then solve the problem. So let's do that quickly. So this is going to be 1 over n. So our n is x, so that's going to be 1 over x into del m del y. So what's our del m del y now? Del m del y is what we have found here already to be 2y minus del n del x, that is 1. So when we divided by this, it is not a function of x. You can see that it has y and it also has x, and this is not cancelling out. So let's check the next one. The next one says what if we divide by m? So let's say we divide by m, that's going to be 1 over m into del m del y minus del n del x. So let's check what that's going to give us. That's going to be 1 over y squared minus y into 2y. I'm checking the second condition here, if it satisfies the second condition, so that we can make this our integrating factor. So this is 2y minus 1 as before. So is this going to be a function of x or y only? Obviously it carries only y, x is not there. So this is going to be our h, we call it h, that's just formality anyway, h of y. So this is a function that depends only on y, so we are good to go. So now, according to what we have noted here, the integrating factor will now be given by e raised to power minus of integral of h of y dy. So that means that our integrating factor can be found. Integrating factor, so function which possibly depends on x and y, is going to be e raised to power minus integral of h of y dy. Alright, so let's quickly do that. So let's write out our h of y in a more compact form. That's going to be h of y equal to 1 over y squared minus y into 2y minus 1. That's just going to be 2y minus 1 over y squared minus y. Alright, so I don't know if you are seeing what I'm seeing, but if you see what I see, you should see that the denominator, when differentiated, will give you this numerator 2y minus 1. So I hope you notice that. So that will help us do some integration directly without having trouble when we get here. So let's do that now. Integrating factor, which depends on x comma y, will now be equal to e raised to power minus integral of this. That's going to be 2y minus 1 all over y squared minus y dy. So I just observed now, as I have just observed something I wish I stated, whenever you have the numerator, whenever you have a quotient of two functions, you need to integrate, and then you have the numerator to be a derivative of the denominator, or you can possibly do make the numerator a derivative of the if you can possibly make the numerator a derivative of the denominator, maybe by multiplying by some constant or dividing by some constant, then it is quite easy. So let me write out that general formula. That means whenever you have